Welcome everyone to today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today we'll be looking at specifically the application of thermal conductivity in the realm of geological material testing and related applications. So in today's session, we will cover a few different methods for the characterization of these materials, as well as go over a few different examples, both some we've collected internally and others that are publications featuring the use of these different methods. So I want to start out with just a little bit of background before we go into the core of today's content. For those that may have watched some of these webinars in the past, you may know this, but for those who are new, C-Therm, really at our core, what we focus on is thermal conductivity. This is our primary focus here, is the characterization of a range of materials, all under the guise of thermal conductivity, specifically using transient methods. So that will really be at the core of today's session, is looking at how these transient methods come into play, where they're most applicable, and of course, going into some examples with that. So our core instrument is called Trident. Trident was developed as a modular platform, so it brings a few different methods together under one roof. The idea here being it's really good to have options. And, as we go through today's content, we will see that depending on, the sample type that you're looking to measure, maybe the conditions that you're looking to test under, certain methods have different advantages in these different scenarios. So really being able to pick the best tool for the task at hand is going to set you up for success in getting the best possible data, whether that's for R&D purposes, developing new materials, looking to compare and do assessments of different material surroundings, and again, looking at the different conditions that might be relevant to those studies. This is a quote we like to use, but it really embodies I'd say the reasoning behind Trident, the modularity of the platform. It's a quote from Abraham Maslow: "When all you have is a hammer, everything looks like a nail." So again, if you're limited in maybe just one method, or if you're trying to make a technique work in a scenario that it maybe really wasn't designed for, that's probably the biggest source of poor data collection that we see. There are a lot of good methods out there, but frankly, they're not all suited for everything. So again, this is really where the ability to pick and choose the best option can really come into play. Now, when we go through here today, I'll be, of course, covering some of the core methods that are available on Trident. But, to go into a really deeper dive and even look at some of the other methods that are out there that are available, we do have a method selection guide, which does go over quite a few of the different options. This is a really nice resource, especially if you're new to thermal conductivity and you're looking to learn a bit more. This is available as a free resource on our website. So please feel free to take a look at that if that's of interest. And also, just as a note, so again, I mentioned C-Therm. We are, of course, focused on thermal conductivity, but we do also work in a range of material characterization with our partners, both at Rigaku and Metrovib, for various other material properties. Specifically, Rigaku focuses on a nice line of thermal analysis equipment. These are things like DSC, STAs, TMAs, and things of that sort. And then Metrovib more on the mechanical material characterization, high force, high frequency applications, fatigue, crack growth, things of that sort. And then also, as a note, we do have a full service test lab, Thermal Analysis Labs. This is a sister company of C-Therm. So, if you were looking to maybe get into thermal conductivity testing, maybe you had some materials that you just wanted to send out for assessment, TAL offers all of our transient measurement options, as well as the other material characterization options from Rigaku and MetroViv as well. So if you have some testing needs, definitely feel free to reach out. Happy to set you up. So yeah, that being said, if you would like to learn more, of course, today's session will be, again, very specific to geology and some relevant applications there. And we'll go through some different examples. But if you wanted to have more of a one-on-one discussion with us, maybe looking to bring some capabilities in-house, definitely feel free to reach out. We're always happy to set up a consultation with you and your team. And also if they're, looking at acquiring an instrument, or again, for testing services, just looking for some budgetary information, always happy to facilitate those conversations. So I'd like to end here with just before we go into the core, a client testimonial. It's always nice to see what our users are saying about us. This is from the Geological Survey of Estonia. User there noting that the Trident has been a helpful toolbox for the lab at the Geological Survey of Estonia, able to test various rock samples, and we are very happy with the device. So always good to hear some positive feedback there. And we do have a range of client testimonials available on our website. Definitely feel free to take a look at that to maybe see if there's maybe some relevance in the type of applications or users that are kind of doing similar testing that might be of interest to you. All right, so this brings us to the core of today's session. We will probably be spending about 30 to 40 minutes or so over the content coming up. As we go through this content, there will be, of course, at the end of the content, we will have a little bit of a Q&A. So if you did have any questions about anything that we're presenting here today, definitely feel free to make use of the chat box feature. And again, we'll have a little bit of a Q&A towards the end of the session. Okay, so kind of to introduce the topic here, really, why is thermal conductivity important in this space? What are the uses and where does it come in? So, whenever we're talking about anything that involves heat transfer, whether that's a specific natural process that is looking to be studied, or more so, and I'd say more relevant to what we're looking at here today, are different applications for things like geothermal site evaluations, different extraction processes, any area where heat is part of that process or that consideration. Thermal conductivity will play a role. And as we go through today's application list, we'll see a few different examples really highlighting where that thermal conductivity data can be really valuable. So all under the guise really here of heat transfer, this is where we're focusing on thermal conductivity. So, why transient methods? Why are we looking at transient methods here? So generally speaking, there are a few main reasons why and some benefits to transient over the more traditional options. The first one noting here is the representative testing conditions. So being able to test a sample just ambient room temperature, that can be valuable, but there are some situations where, again, maybe you're looking to test under a specific temperature as it relates to the the surrounding body or the in situ conditions that you're looking to represent. Temperature will be a big one we'll look at here today. Also aspects of different pressure. When we look at different applications in the geological sector, different depending on where you're looking, whether it's just at the surface, maybe you're going a few kilometers into the ground for different extraction surveys. You're changing some of those environmental properties or of interest. So the transient methods that we offer, many of them do come with the ability to play around with some of those conditions and really push it into some more novel testing ranges outside of just your, call it your basic ambient setups. The other last 2 points here, looking at the speed, transient measurements will always be faster than traditional steady state options. This can again be quite valuable. Time is money. So depending on, again, maybe the amount of materials you're looking to test, of course, projects have deadlines, so you want to be able to effectively use your time. Transient options provide a nice fast pathway to that. And then the last one is a very great, really greater flexibility on your sample size, your sample format. So whether you're looking at maybe the solid kind of core samples, different liquids or fluids that might be involved in these processes, powders, for example, even, there are different setup options available there. So again, the transient methods provide some nice options there, especially when you're dealing with a very dynamic application space. So the first method we'll take a look at here today and some examples with it is the MTPS, or Modified Transient Plane Source. So you can see a picture of the sensor on screen. This is a single-sided device for the measurement of thermal conductivity and effusivity. The MTPS will be the one that's, I'd say, most heavily featured here today. You also note the application of high temperature and pressure capabilities. So we'll go into some examples with that, with the MTPS in mind here to start. This is just a quick snapshot, but one little example. There's no data here, but one user of ours, the Seaforth GeoSurvey Inc., they actually, you can see on their onboard research vessel, will be using the MTPS for testing some of the extracted samples. Again, the sensor, very versatile in the environments that you can place. It's great for a research benchtop application, but it is quite portable. And you can see some examples here testing some of these core samples that are coming out from the extractions. So again, kind of one example of another user of ours and where they're employing the technology. More of a, I'd say, a little bit more of a novel application of the MTPS is the use of the high pressure cell. So this is a picture of the MTPS high pressure cell setup. So with this configuration, again, you're able to control the pressure of the environment that you're testing in. So your samples would go inside of this device. You can subject that to different, whether it's gases, nitrogen, argon. Also, some groups will be looking to pull vacuum and do some testing in those types of conditions as well. But I have a couple examples here coming up looking at the use of the MTPS high pressure cell in kind of the data that you can collect with it. So the first one here is on some bitumen testing. So when we're looking at the application of bitumen, so bitumen extraction in particular, these are generally very, deep reservoirs. There's a thermal process used to essentially remove the bitumen from the ground. It's pumped out through steam injection processes. And when we're talking about, again, anytime where heat comes into play, the heat transfer properties, those thermal properties of not only the oil sand play a large role here, but also the surrounding materials. You really have to understand the different constituent components and how that introduction of temperature will impact those systems, whether that's from a process optimization standpoint, from safety considerations or things like this. Also on that, the composition of what you're dealing with, is it saturated? Is it dry? These can all impact how effectively these materials can be obtained. So again, trying to mimic those representative conditions can be quite important. So taking a look specifically at the bitumen sample itself, these are typically very heterogeneous materials. They have kind of a range of constituent components, but ultimately here they contain different entrapped materials, water, gases, things of that sort. But the thermal conductivity of the specific bitumen samples, they can vary depending on the composition. So we have one kind of example here that we'll present of a sample that was tested in-house here with the MTPS. And, a very kind of, I'd say, straightforward data set to present, but really just kind of demonstrating thermal conductivity as a function of temperature. So this was done with the high pressure cell under a pressure of about 700 PSI. I believe this was to replicate some desired conditions of a project that was worked on. But we can see here that the thermal conductivity does vary as a function of temperature. So in this case, we're noting a noted decrease with increasing temperature in this example. But again, just one little snapshot of how these types of samples can be tested, specifically here with the MTPS high pressure cell. Another area where we've seen some application of the MTPS, and again, the pressure testing options, is when you're looking at enhanced oil recovery or geosurveying of some of the surrounding materials. So maybe it's not necessarily a sample you're looking to extract, but really looking at what's happening in the surrounding area. So again, the thermal conductivity of these solid materials can play a significant role in the different designs of these systems. Again, from how they're able to handle the thermal load, the stress that's being introduced during these processes. Again, the thermal considerations play a role. So understanding thermal conductivity of the different materials that are going to be surrounding or involved can be quite important. And again, here we're looking at a sample that was tested under, again, varying temperatures, but the same material tested under two different pressure conditions. So one really zero pressure, call it your ambient conditions, and then under 2000 PSI. So again, just looking at the trend overall, regardless of the pressure condition, we see a decreasing thermal conductivity as a function of temperature. But again, looking at some of those data points, specifically kind of at the initial point there about room temperature and then up to 100 degrees, there is a difference in that effective thermal conductivity based on the pressure condition. So again, these differences based on the conditions that you're looking to represent can have an impact on that thermal conductivity. So, in examples where maybe some of this data is being put into perhaps modeling of some of these systems or processes, that difference of, say, 3 watts per meter Kelvin versus, 3.54, that could potentially be lead to some significant influences on the overall outcome of those studies. So again, the representative testing conditions matter. So, that was a few examples on the MTPS. And again, we see quite a lot of use case with the MTPS in this application. One of the other methods that we'll take a look at here is the more traditional flex transient plane source, or TPS for short. Now, the TPS is, as you can see just by looking at the image of the sensor on the left, quite different in its overall design. It's a double-sided sensor. It's thin. It's flexible in nature. And with the TPS, there are some advantages that you could obtain depending on the type of sample that you're testing. And I'll kind of go into some examples with that here. So specifically any, porous material, there's of course many porous geological samples that can be tested. With the TPS, there is no requirement for a contact agent. That is something that some methods do require, and of course, if it's porous, if it's hygroscopic, going to absorb that contact agent, the TPS is a great option for testing those materials because that's not needed. If we're looking at one of the other methods that we'll take a look at later, the TLS, some of these materials are quite hard, rigid, can make it more challenging in those types of setups. So again, with the TPS, very thin and flexible, makes it a nice option to test this class of sample. So with the TPS, you can see just a very generic setup here, but you have your sensor between two materials, and you could basically create this sandwich stack around the test. Around the sensor probe itself. And again, no contact agent needed here is the big takeaway. So again, for a sample that would again potentially absorb that contact agent, TPS avoids that completely, making it a really nice option. So when we look at the thermal conductivity of some of these materials, we can see quite a wide ranging. So looking at here at pumice, thermal conductivity on the low end, 0.1. on the high end been noted to be up around 1.4. So in really all of these examples, the effective thermal conductivity will depend on the moisture, the composition, the porosity, and unlike I'd say a lab synthetic generated sample, which are quite consistent, in some of these more naturally occurring bodies, you can have quite a lot of variability, which can, of course, be really important to take note of. Again, similarly here, an example on sandstone, kind of the low end 1.8 versus some data collecting showing upwards of 3.9. Again, all related to those differences in the composition and some of those conditions of interest. And the last one here, another one looking at the low end, so tough 0.04 versus 4. So almost an order of magnitude difference in some cases. And the other thing, as you can see just by looking at this image, the overall heterogeneity of the sample. So depending on the TPS sensor that is employed, there's actually some different sizes. So being able to use a different sensor size will change the effective evaluated volume. So again, sometimes picking a specific size depending on the material you're working with can provide some benefit or insight into the effective measurement of those materials. All right, and then next up, we're looking at the TLS, or Transient Line Source. So this one here, you can see again, very different in its design. This is a needle probe style sensor, capable of, again, providing thermal conductivity as the core output. But our TLS does conform with some high temperature and high pressure testing capabilities. There's some novel application there. And I will just flag the ASTM D5334 standard. This is one that is related to geological core soil sediment samples. We've seen this referenced quite a bit as well. There is a dedicated ASTM specific to that application space with this technique. Wanted to give one quick little highlight here, testing potting soil, looking at the influence of the packing and the saturation. So again, depending on, the material, those considerations like how dense the sample is it dry, is it partially saturated? This can have an impact on the effective thermal conductivity. So taking a look here at just some data set that was collected, initially the far left there, just the loose sample, essentially just unpacked, coming in just shy of 0.1 watts per meter Kelvin. When we take that same sample and then pack it, so apply some compression, densify it, we do see that spikes up. So the increase in thermal conductivity noted there, about 35% compared to the loose sample. Then when we take that pack sample, and again, looking to mimic a specific saturation level, so we're adding some moisture into that evaluated material, we see another increase, about 22% there. So again, just kind of indicating that depending on not only just the material that you're working with, but if it is compressible in nature, if it could be densified, controlling for that and again, representing the conditions that are relevant to the application can be really crucial to get the best quality data there. So that was a little bit of, I'd say, a run through on some of the methods and some kind of a few example data sets. But going into the final portion of today's presentation, wanted to do a little bit of a overview of some publications that have been made use of the various methods that we have available on the Trident platform. So this first publication is called The Study of Different Grouting Materials Used in Vertical Geothermal Closed Loop Heat Exchangers. So this is some work coming out of Spain. This was published in the Applied Thermal Engineering journal there, using the MTPS method. So typical ground coupling options for these geo-exchange systems, there's a few different options there you can see on screen. The vertical one is what we're looking at here today. But of course, there are a variety of options there, depending on, the environment, the area that is being employed. Of course, there are certain benefits and advantages to each here. But this is what they were focusing on primarily in the study, was the vertical systems. So this was all used for the geothermal heat exchangers. So this is a topic that it's been around for a while now, but we're seeing it very, I'd say, pop up more frequently, especially with the application of really trying to find more effective ways, looking at, call it more greener energy initiatives. Geothermal is something that is definitely popping up in popularity across the globe. So what these do are essentially, they make use of the inherent temperature differences that occur during winter and summer. So in the winter, they're using the warm energy, the heat thermal energy that is available to heat up the buildings and houses. And then, of course, in the summer, when it's really hot outside, kind of switching that and looking to use some of the more cooler options. But when we're looking at these processes, looking at heat exchange, the warm versus the cold, again, this is where the thermal considerations of those surrounding materials can play a role in the overall effectiveness of that heat transfer, to really, again, looking at optimizing some of these processes. So when they were looking at the vertical geothermal installations, one of the impacts and one of the considerations involves some of the, I'd say, construction and some of the materials that are actually being used in conjunction with these natural systems. So there is a geothermal grout that is employed. Depending on the design and the specific requirements that you're looking at, these grouts can come in to enhance the thermal conductivity based on the additives that are employed. So there are some typical options like silica sand is generally a common use case, but there are certainly some additional materials out there, and this is what they were actually looking at in this study. But here you can see kind of an example installation process. You're essentially drilling that hole, feeding in those geothermal loops, and then the grout or that seal is what's, again, kind of enclosing that system. Looking at a cross section here, this is what that looks like. Again, that heat transfer medium is what's going to be moving that thermal energy around during the delivery of the heating or the cooling. So what they were looking at specifically in this study were 4 different aggregates to see which one had the best impact or largest effect on the thermal conductivity of that grouting system. So there's the traditional silica. They also looked at limestone, a furnace slag, as well as some waste products being repurposed into this application. And we can see here, looking at some of the data that was collected, looking at the thermal conductivity based on the total aggregate to cement proportion by weight. Overall, the silica sand did have the highest effective thermal conductivity across all of those tested weight mixtures. But again, just kind of shows the comparison of where, which options might be beneficial. And of course, this is just a snapshot of the thermal conductivity side of things. But the other aspect whenever we're dealing with a filler is, how is that affecting some of the other properties, perhaps the mechanical or the structural considerations as well. So again, there's a balance that always needs to be taken into account. But ultimately here, looking purely at thermal conductivity, that silica sand did result in the highest effective output. So in this next example here, this is actually some nice work. This was published at a conference, so the 9th International Conference on Mars. So looking at actually some applications of looking at the thermal measurements of some of these Mars rock analogs. So, we think of geology, of course, a lot of it's focused here on planet Earth, but with all the exploration going on and looking at potential applications of, how are these materials, how are those properties changing in very different extraterrestrial environments? There's been some work recently looking at some use cases for materials that are on other planets, such as Mars, for example. So this really all set off with the NASA's mission to Mars, really trying to understand more about the geology and some of the applications. But with, again, looking at a very new areas, there are a lot of unknowns. So this work was done specifically to characterize materials under conditions representative of Mars's atmosphere and pressure to see how that influences the thermal conductivity of those systems. So this was a kind of a snapshot taken out of the publication here, but they were using the noted there as a Mars simulation chamber. So that's the MTPS high pressure system. And then they were pulling vacuum under different conditions to test the thermal properties of those samples. And here they're really focusing on the thermal inertia or the thermal effusivity versus the porosity of some of those materials. But we can see that, again, depending on, if it's a more dense, less porous sample, typically you'll see a higher effective thermal effusivity, thermal conductivity. And then as that porosity increases, you kind of see the trend that is frankly expected. But again, just some examples and use cases of where these methods are being employed in some more novel options and ways. And then the last one here, this was a very, I'd say, collaborative study. This had researchers from Italy, Germany, Greece, Ireland, Switzerland, all coming together looking at the title of the paper was an updated ground thermal properties database for GSHP applications. So this was published in the Journal of Geothermics, and again, using the MTPS for the core method of investigation. So ground source heat pumps, these are again related to, energy storage, thermal energy, providing heat in the winter, cooling in the summer. Now, the higher thermal conductivity in the ground and those surrounding media ultimately results in better heat transfer efficiency and better overall performance. So when you're surveying different areas to essentially assess the fit for these types of systems, again, the thermal conductivity, the thermal properties of those surrounding bodies play a significant role. This was actually just a little excerpt that I took out of the paper. They said the most important thermal characteristics of the local underground to be taken into account when designing these systems, it's thermal conductivity, heat capacity, and thermal diffusivity. So, of the most important ones, thermal conductivity is listed as a primary consideration. And again, what this data essentially is used for is to provide these maps. So an example, that thermal data that is obtained can then be transferred to geothermal potential. And, you can use that to assess where these have the best fit, where they're most attractive, to see if really introducing these into these areas is going to be effective at, solving the problems or the issues that are at hand there. And again, with geothermal popping up around the globe, there's a lot of land to cover to really kind of cite out which is the best overall options there. But here we can see some of the thermal conductivity results that were obtained by the MTPS. And this was a really in-depth study. They looked at quite a range of materials and then compared it to the literature values of those samples. And what you can see is, again, with some of these naturally occurring, the literature values can be quite a wide ranging. What you can see in the gray bars there, those little X's are indicative of what is generally accepted as the most common thermal conductivity value associated with that sample type. And then the colored bar are representative of the MTPS data. So, you're looking at everything from sandstone, limestone, you can see that going across there, but generally giving you an idea of where your samples are falling with respect to some, expected values, but then also just understanding the inherent variation that can occur in some of these systems. All right, so that's coming up on the end of today's session. Like to take a moment and thank everyone for your attendance here today. Going through a final housekeeping items here before we go into the Q&A. If you're looking to get more information or maybe see some additional resources, there is an extensive library of past webinars as well as technical content available on our website. Definitely feel free to take a look around there to see if there's anything that sparks your interest. If you're looking to keep up to date with us, maybe keep up on new blog posts, upcoming webinars and events, definitely the best place to do that is on LinkedIn. So give us a follow on there. This is where we'll be able to update you as in real time to new developments and anything new coming out that you should be aware of. As far as upcoming webinars go, a little bit different from today's topic, but we do have a featured guest speaker webinar looking at the thermal effusivity test development on sportswear fabrics. This is with some guest speakers from the University of Alberta. This will be August 22nd, so about a month from today's date. Also, looking at some upcoming events. So if you're in the area and you're looking to discuss or maybe want to stop in and chat, definitely feel free. We'll be at NATIS, the North American Thermal Analysis Society, September 16th to 19th. That's going to be in Knoxville, Tennessee. And then a little bit later on in the year, we'll be at the Battery Show North America, October 7th to 10th, which is taking place in Detroit, Michigan. All right, so that brings us to the end. We'll go into the Q&A here. If you did have any maybe specific questions, definitely feel free to reach out, info@ctherm.com. We'll be able to address your questions in further detail. But again, with the remainder of the session here, we'll close out and go into a more of a Q&A with the audience. So if you're interested in sticking around for that, please feel free to do so.